2-point charges Q1 and Q2 are on the x-axis. Q1 is at the origin, Q2 is 3 centimeters to the right of Q1. We want to calculate the electric field due to each charge at point P, which is located on the y-axis 4 centimeters above Q1. So the geometry is given, the charge on each particle is known. The distance R1, distance between Q1 and P is known, that's 4 centimeters. The distance between Q2 and P is not given, but we can calculate it using the Pythagorean theorem. Using the 4 centimeter and the 3 centimeter, the horizontal distance, R2 is the hypotenuse, and I have that on the board. It's a 3, 4, 5 triangle. If you calculate the hypotenuse, R2 is equal to 5 centimeters. So we want to calculate E1 and E2. As shown on the picture, E1 is a vertical vector. It's pointing towards Q1. Q1 is a negatively charged particle, so the electric field that it's creating, it's pointing towards itself. Vector E1 is going to be basically equal to E1, negative E1 J hat. Like so. How do I calculate E1, the magnitude of the electric field? I use the electric field formula for point particle. That's K times Q1 divided by R1 squared. Note that I'm using the absolute value of charge Q1 because I have already determined the direction of vector E1. It's pointing down, so I have used the information that Q1 is a negatively charged particle. Now K is known as Coulomb's constant. Q1 is given, R1 is also given. If you plug in the numbers, here's what you get. Negative 2.81 times 10 to negative 4 newtons per coulomb J hat. That's E1. Now let's calculate E2. Vector E2, as you can see on the picture, is making an angle. The angle between E2 and vertical, I call that angle alpha. We are going to find the components of vector E2. So E2 has an x component and a y component. From the geometry, we can see that the x component of vector E2 is negative, it's pointing left, and the y component of E2 is positive. In terms of the magnitudes, the x component is going to be equal to E2 times sine alpha, and the y component is going to be equal to E2 times cosine alpha. Now, do I need to calculate what alpha is equal to? You could calculate alpha because, again, the geometry is given. If you focus on the large triangle, so if you focus on the triangle that I shaded in green, you will see that cosine alpha is equal to R1 divided by R2, that's 4 over 5, and sine alpha is equal to 3 divided by 5. And as I mentioned, the x component of E2 is equal to E2 times sine alpha, whereas the y component is E2 times cosine alpha. So I'm drawing this vertical dashed line in the green segment. If you focus on the upside down triangle on the top, the green segment represents the x component of E2, and that's the opposite side of angle alpha, so that's alpha, E2 times sine alpha. So vector E2 is equal to negative E2 sine alpha I hat plus E2 cosine alpha J hat. Let's apply again the electric field formula for a point particle. And this is how we can express E2 in terms of the given variables. Now let's go ahead and plug in the values and calculate the components of E2. And here's the result we get for E2. when we plug in the numerical values. Negative 0.647 I hat plus 0.863 j hat. I have an overall factor of 10 to negative 4 power, so I put the two components in parentheses and I have the factor of 10 outside of the parentheses, and the unit of course for both components is Newton per Coulomb. So that was part A. Now in part B, we'd like to calculate the net electric field at point P. So we'll basically go ahead and add the two vectors, vector E1 and vector E2. Because we already have our vectors in unit vector format, it's very straightforward to add them together. We're going to add the two vectors component by component. So we're going to add the x components together and the y components together. So here I have plugged in the numerical values. I have three terms. The first term, negative 2.81 j hat, that's vector E1. And then I'm adding vector E2. The next two terms are the x and y components of vector E2. Again, I have an overall factor of 10 to negative 4th, and the unit is Newton per Coulomb. So I have two terms with j hat. I'm going to add these together, and I only have one term with I hat. That one remains as is. And that will be our final answer for the net electric field vector. So when we do the calculation, this is our final answer. Net electric field vector at point P is equal to negative 0.647 I hat minus 1.95 j hat times 10 to negative 4 Newton per Coulomb.